We already know from Newton's first law that an unbalanced force is required to change the motion of an object. In other words, in order to cause acceleration, you have to have some kind of net unbalanced force acting on an object. Most of the time, forces act over a period of time. Even if you have something that seems to happen very suddenly, like a baseball bat hitting a baseball, if you slowed that down to to watch it in very, very slow motion, you would see that as the bat comes around, the bat and the ball are actually in contact with each other for a brief period of time. And whether that period of time is very brief or much longer, like when we see a rocket ship lifting off over several minutes, a force that's applied over a period of time is called an impulse. And an impulse is also defined as a change in momentum. An impulse is a vector quantity, just like momentum is a vector quantity and force is a vector quantity. Impulse is the product of the force acting on an object and the time interval. So the impulse is equal to force times delta t. It's the time interval is the amount of time during which the force acts on the object. Time, of course, is a scalar. It does not have direction. It just has a magnitude. And so impulse is a vector times a scalar. When you multiply a vector times a scalar, you still have the direction of the vector. So the formula for impulse is I equals F delta T. We also see this expressed as delta P equals F delta T because impulse is defined also as a change in momentum. So a change in momentum over a period of time, delta P is equal to F delta T. It's a very useful equation. Here we see a pool ball that is rolling toward the edge of a table. Now, when the ball hits the edge of the table, it's going to bounce off. Before the collision, we see the ball rolling toward the cushion, and then after the collision, we see the ball rolling away from the cushion. In your reading, you see a short paragraph, and you have to keep this in mind. The positive direction is to the right, the negative direction is to the left. So before the collision, we see that the pool ball is moving in a positive direction toward the right, and then after the collision, we see that it's moving in a negative direction toward the left. When you complete that sentence, or that paragraph, I'm sorry, in the book, it'll look like this. The momentum of the ball is its mass times its velocity. After hitting the edge of the table, the velocity of the ball changes from positive to negative. As a result, the momentum of the ball changes from positive to negative. So if the momentum then is in the same direction as the velocity, because remember, momentum is equal to mass times velocity. So the momentum is in the same direction as the velocity. You also see a little note that the initial velocity is positive to the right, the final velocity is negative to the left, as I mentioned before. Because velocity is a vector quantity, the sign changes to indicate the direction change. And because the velocity changes from positive to negative, the momentum also changes from positive to negative. So before the collision, the ball is moving in the positive direction, its momentum is in the positive direction, and after the collision, its velocity and momentum are both in the negative direction. So what's happening during the collision? During the collision, we have an impulse. We see there's a change in momentum, right? The momentum is changing from positive to negative, and that change is taking place over a period of time. Because when the ball hits the cushion gets compressed a little bit. It's like a spring. We've seen diagrams where a ball rolls into a spring, the spring compresses, and then it expands back out and pushes the ball in the other direction. The same thing's happening on a pool table, even though it's happening at too quickly and at too small a scale for you to observe it as it happens. So when the pool ball hits the cushion compresses, and the ball then accelerates toward the left. In other words, its velocity is to the right, its acceleration is to the left, and so it's slowing down. And then the cushion expands back out. So the cushion pushes the ball back out. It continues to accelerate to the left, but now the velocity is also in the negative direction to the left, and so the ball speeds up as it rolls away. What net force acted on the ball in the images when it hit the edge of the table? Describe delta T in this scenario. Okay, I just talked about that. The net force acting on the ball is the force of the cushion pushing to the left. We, of course, also, if we were to draw a free body diagram of this ball, we would also have gravity pulling the ball down. We would have the normal force of the table pushing the ball up. And then we would have some friction working, pushing the ball in the direction opposite its velocity. The delta T is that very short period of time where the ball is in contact with the cushion, and where the cushion is compressing and then expanding back out, pushing the ball away. So what could be changed to reduce the force on the ball while still having the ball experience the same change in momentum? Well, if you want to exert less force but still get the same change in momentum, what you would have to do is increase the time over which the force is applied. Because remember, change in momentum, we see this up at the top of the up at the top of the slide here. F delta T equals delta P. So if we're going to say delta P is constant, okay, we have the same change in momentum, and we want the force we want to use a smaller force, then that means delta T has to be longer. So you have to have a longer period of time. Smaller force applied over a longer period of time is going to result in the same change in momentum. How could you do that? Well, maybe instead of you would change the material of the cushion, maybe even put a spring there so it compresses and expands over a longer period of time. Okay, in an isolated system, this is a new definition. You should add it to your notes. An isolated system, or a closed system. In an isolated system, there are no external forces acting on any of the components of the system. Okay, no net external force. That means that if there's no external force, then that means that Newton's first law is going to apply, right? If the object's in rest, it's going to stay at rest. If the object is in motion, it's going to stay in motion at a constant velocity because there is no external force. So in an isolated system, that means that there are no forces from outside that are acting on any of the components of the system. If we ignore friction from the surface of the pool table and we ignore air resistance, so we're ignoring all friction forces, and you have two billiard balls or pool balls crash into each other, that would be an isolated system, because the only force, if you ignore friction and air resistance, the only force is the force of those balls hitting each other. So ball A hits ball B hits ball A. You have an action-reaction force there, force pair. Let's look at the question. Define the billiard ball and the edge of the pool table as the components of the system shown in the three images. Is it an isolated system? Is the total momentum of the system conserved after a collision of the billiard ball and the edge of the pool table? It means, does the total momentum stay the same? And in this case, we cannot say that total momentum is conserved, because the momentum of the ball changes, right? It changes from positive to negative. We don't know the values. We don't know positive how much or negative how much, but the momentum of the ball changes, but the table doesn't change its momentum. So when the ball hit the cushion, if the cushion gained that momentum that the pool ball was losing, then we could say that was an isolated system, but that's not what's happening, right? The cushion isn't gaining momentum. That's why if you have two separate pool balls, when one ball hits the other, the first ball might lose its momentum, but then the second ball will gain its momentum, will gain the same amount of momentum. That's momentum being conserved. In this case, momentum is not conserved. So that means that this is not an isolated system, and there must be a net external force. So if there is an external force, where is it coming from? We have the edge of the table. The pool ball is hitting the edge of the table. The edge of the table is connected to the rest of the table, and the rest of the table is sitting on the ground, and there's a friction force keeping it from sliding. There's static friction, right? Keeping it from sliding across the ground. And so that's where your opposing force is coming from. It's coming from the table pushing back on the cushion, the ground pushing back on the table. And so we see only the momentum of the ball changing because what was drawn in that image on the previous slide was not an isolated system.